Okay, so good morning, everyone. Today we have Shubham Bharadwaj, who will be representing his master thesis, whose topic is probing gas in the merged halos of a pair of galaxies. Shubham Bharadwaj is from Aligarh, Uttar Pradesh. He has done his master's in astronomy and astrophysics from Indian Institute of Space Science and Technology, IIST Kerala. So I hand over this to Shubham so that he can continue.
Basically, on large scale survey, it's basically a study of baryonic matter. Like we have a direct observable component of our universe, that is the ordinary matter, or known as the baryonic matter, which is decomposed in this pie chart. This is taken from PSO website. The numbers are not accurate. They come with some error bars which are not shown here. So what we know is, like, from very high redshift to present, most of the baryons are residing outside the galaxies in the intergalactic medium or in the circumgalactic medium. So in a very high redshift universe, something greater than 3 or 4, so only about less than 22% baryons are present inside the galaxy. Most of them, like about 98%, resides inside the intergalactic medium or circumgalactic medium. So over that time, that's to present, it's about 10 to 11 billion years. So over that time, some baryons have moved inside the galaxies to form collapsed structures. Like structure formation is happening, like to form stars, galaxies, and so on. But still, only a few percentage of baryons have moved towards the galaxies to form collapsed structures, and this is observationally established. So from this, we are sure, like, the galaxy formation is relatively an inefficient process, and still high percentage of baryons is residing outside of galaxy outskirts. Like we can see, the stars in the galaxy only comprise of 7% of the baryonic matter. This cool gases in the galaxy comprise of 1.8. So the hot gas, which is outside of galaxy outskirts, like in the halos of the galaxies, it is residing only 5%. So we can see a large percentage, it's 40, 28, 15. If we add up all this, it's a very large percentage which resides outside of the galaxy. So if we only focus on, like, studying the bright objects like stars, galaxies, etc., so we are just probing only a very small chunk of baryonic matter. So that's why it is important to study intergalactic medium or circumgalactic medium, because they are the major reservoirs of baryonic matter. That's the only observable component to study our universe. So that's why we look outside of galaxy and study the baryonic matter. You can see the slides.
Yes.
So the motivation for this study is, like, this is a very broad, large scale survey. So what I did in my project, we have took a small chunk of that large survey, like that can be chewed easily in 1 year of project. So since I mentioned that most of the baryons in the universe are residing in the intergalactic medium and circumgalactic medium, so this is what actually is happening. Galaxy basically accretes. This is the intergalactic medium. So galaxy accretes uh, gas from the intergalactic medium in their circumgalactic medium, which spirals down into the galaxy via accretion. It's accreting gas, which triggers star formation and which helps in the evolution and growth of the galaxy. So galaxy. So this is the accreting part. Like this is how the galaxy is taking gas outside from its environment, that is from the intergalactic medium. But then a recycling process happens, like there are supernova explosions and other outbursts happening. So this gas flows outside, that outflows happens, and that's how this galaxy again gets into the circumgalactic medium, and there is a continuous interplay between this intergalactic medium and the circumgalactic medium. So galaxy evolution and its formation depends on how this inflows and the outflows are interacting with the galaxies. So dynamics of this inflows and outflows dictates the evolution of galaxy. So that's why it is important to study this gas, which is the diffuse gas uh, comprised of the baryonic matter, because it relates our connection with the galaxy, and it's a very uh, key understanding to the evolution of baryonic matter. So what my project is, the broad goal of the project basically to understand the multiphase. Since this gas is outside, so it can have a multiphase. Like it's not uniform. If we probe along a one line of sight, we see some properties of the parcel of gas, like some temperature, some density, some uh, ions to be present. But at the different side of line, for the same gas cloud, we see some different temperature. So that means that the gas cloud overall is not uniform. It has a multiphase property. So what my project is to understand this multiphase property associated with this disk and halos of the galaxies, and also to see whether the absorption systems of high hydrogen column densities can be used to discriminate these inflows and outflows. So this is a schematic diagram which shows how the work is look like how what's the principle of quasar absorption and spectroscopy, the technique we use to study these absorption clouds along the line of sight. So what it does, like from earth or from space, we probe QSO, like we are the telescope is pointing towards the QSO, for which it's a point source. So this is our line of sight, and uh, this is a very bright quasar, and this is a gas cloud which is associated to a galaxy. Like what I've shown here, the galaxy is here and the clouds are residing here, which are continuously interplaying with the galaxies. So intergalactic medium and circumgalactic medium. So this gas cloud is a diffuse gas cloud associated with the galaxy. So when the light comes from this quasar, when it passes to this gas cloud, since we know that quasar is a very bright source, it will have its continuum and some prominent emission lines, broad emission and narrow emission lines. But we are not interested in that. What we are interested is in this gas cloud. So when the light passes through this line of sight and there is a gas cloud between us and the quasar, it absorbs uh, some light of this quasar, like selectively absorbs some light depending on its configuration. Configuration, what I mean, like uh, what metal ions are present, how much metal ions are present. So it depends on the chemical composition and column density along the line of sight, and the ionization condition in the gas. So, so to study the absorption line, uh, we infer the constituents of this gas, like how much hydrogen is there, how much metal ions are there, the physical state, and then we will study the chemical composition as well. So, as I mentioned, this cloud is a part of the ISM of the galaxy. So, so this part of the cloud, we'll call it as a phase structure, like it has different densities and temperatures. So what we call it as a different phase structure, like a multi-phase composition. So what it looks like when we get an absorption spectrum is this. So what my project is to study a damped Lyman alpha absorber. These are absorption systems which with the high action column is greater than 10 to the power 20.3 per centimeter square. They resides mostly inside the bodies of galaxies and like trace neutral regions of galaxies where star formation is prominent. So my project is to study uh, this background quasar. Like the quasar which I have chosen is this x0206 minus 0438, which is the redshift of 1.128. As I mentioned, it's at a high redshift, and this is the absorber, the gas cloud, which is a redshift of 0.39047. So this particular absorber, which we identified along our line of sight of a background high redshift quasar. So we used spectroscopic data for to study this parcel of gas which comes from cos HST from far UV channel, which is from 1150 to 1775 angstrom. So, but since we know that this parcel of gas is related to the galaxy, so it is important to study the galaxy properties as well to correlate how the gas and the galaxies are interplaying and how they are correlating with each other. Whether we can explain there is a correlation in between that. So for galaxy data, we use MUSE data, which is a multi-unit spectroscopic explorer on very large telescope. Coming to the project, I'm not going to give the details of the instrument that I've used. So this is the quasar spectrum that we use. We can see there is a sub. So it consists of a host of Lyman series lines and Lyman break. I will tell what Lyman break is in next few slides. It is showing a sub DLA, prominent sub DLA. Sub DLAs are another classification of high absorption hydrogen systems, which is a absorption system corresponding to 10 to 19 to 10 to 20.3 per centimeter square. They resides mostly in extended halos of galaxies. So there is Lyman alpha, that is a first transition of H1, Lyman beta of this sub DLA, and the higher order Lyman series lines are there, and there we get a Lyman break. So expanding this spectra, we see something like this. So these are the absorption systems, different hydrogen lines with their different absorptions, H1 926, 923. There are higher lower order transitions as well. So what this Lyman break, this blue line is the Lyman break. What this Lyman break corresponds to is like, since I've told like when a light is coming towards us and there is a gas cloud in between us, so it will absorb, like selectively absorb some of the light, and that's how we are getting an absorption system. But at a certain wavelength, like around 912 angstrom, all the photon energies get absorbed. Like that's a 13.6 eV electron volt of photon energy. It gets absorbed by the hydrogen at 912 angstrom, and at that wavelength, almost all the flux reaches to zero. Like you can see, there are flux values, and this is going almost zero. Sudden drop in the flux, which is almost zero. So this is what a Lyman limit break is. What it helps in, it helps in calculating a lower limit on the column density and the optical depth. Okay. Optical depth in the sense like how much the cloud is optically thick. Like if the optical depth is less than 1, we say the cloud is optically thin, and all of the photons are able to reach us. Like they can penetrate through that cloud, and we are able to see those photons. But if the optical depth is very high, like greater than 1, like as mentioned here, it is greater than 6, and the cloud is very highly optically thick, that means all of the photons are captured inside the cloud, and we are not able to see any photons coming out of that cloud. So that's why there is no flux here, like almost zero, not exactly zero. Not going into the detail like how we calculate it. It will be too technical. So then we slice different regions of the full spectrum of the QSO to see features of the different lines like individual features of different lines, metals, and hydrogen lines of this sub-DNA. So here are the system plots, which show different Lyman series. Not all of the Lyman series lines are shown here. Some are shown here. So this is Lyman alpha, Lyman beta, Lyman delta. So this is the y-axis is normalized flux. How we calculate is normalized flux, like first we do a continuum fit to the spectra and then we divide the flux with the continuum. That's how we get the normalized flux. And this is the velocity in kilometers per second. This is basically a conversion of the redshift. This basically represents the redshift because this zero corresponds to the redshift of the absorber, that is 0.39047. So by looking at these system plots, these are the very initial steps to start our study. So we can see that hydrogen spectrum, this absorption feature is highly saturated. Saturated in the sense we are not able to distinguish like how many component structure it has. But when we go to higher transitions of Lyman series, like here, we can see some component structure, like a two component structure present there. Since these are not that saturated, these are defined very well. So to define a component structure, what component structure is like, we need to fit these lines with some profiles to get some physical parameters. I'll come to that. How we will do the fit. So you can see like these are some other absorption features which are not associated to our line of sight. These are some other contaminations. So here are some of the metal lines. So clearly we can see a two component structure here and a two component structure in this oxygen 2 as well. So to fit these lines, mostly the hydrogen lines, since these are highly saturated as I mentioned, so we mostly rely on the higher transitions of hydrogens to see what the component structure of this absorption system is, how many components are required to fit these absorption system, and plus to get a minimum number of component structure, we look at the metal ions. Like clearly we can see here there are two component structures which we can fit very well. I'll show the fit. So, so these are the wide profile fits. Wide profile fits are the like, fitting routine. It's a fitting routine. The software is available. That's known as VP Fit, and other softwares are also available. What it does, it fits a profile, which is a combination of broadenings of line. Like there are two types of broadening, natural and thermal, which are also known as Doppler. So it fits a combination of profile, which are natural and Doppler broadening. So we can see there are different components to try to fit. Like if we see only the red component, yeah, this blue one is the blue component we see. We are not able to explain the absorption feature properly, and only along with two, like if you try to fit only a single component, that is two, then we are not able to fit this right component of the absorption. So that's how we concluded that we need a two component structure, and also we see in the metal lines. So to properly explain the absorption feature, like to fit the absorption feature properly, what we see, we need a two component. Like we see here, the two component is very well defining the absorption feature we are seeing. So one point to notice here is like the higher order transitions have two component, but the lower transitions have three component structure. This is because like when we tried to fit this lower transition with a two component structure, the final composite fit was not able to explain the leftmost component, that is this wing, left wing, the bluer wing of the Lyman series, Lyman alpha and Lyman beta. So that's how we find that there is a scope of a third component to properly explain the absorption feature in the left wing as well. But since we can see this is quite broad, but it is not that prominent. Even for Lyman alpha, it is a marginal feature. You can see it's very marginal. So for higher order transitions, it's almost gone. That's how the third component is not visible in the higher order transitions. So this third component basically corresponds to another class, which is a broad Lyman alpha absorption line, which we assume that it comes from like it is driven by winds of accretion process close to supermassive black holes. So these are believed to generate in warm hot intergalactic medium. So from these two component structure, the component structure of hydrogen is inspired. Like you can see, it showed the table of results. Like you can see, in the hydrogen we use three components. This component 1, 2, and 3. And what's the common feature we see? This component 1 of hydrogen is coinciding with the component 1 of silicon 2. The second component is coinciding with the carbon 3 second component. And component 3 is coinciding with this oxygen. So that's what I mentioned in the initial phase. Like we look at the metal lines as well to see clearly, because metal lines are not saturated. You can clearly see a component structure. That's how we are getting a component structure here. So these values are not that much required for this. But I can tell you what column density is. Column density is basically telling the number of atoms or ions present our line of sight, which are responsible for these absorption systems, which are responsible for this absorption feature. So this column density is telling this amount of hydrogen is present in the component 1, like in this component, which is having a bulk of hydrogen, which is responsible for this absorption feature.
Can I ask you a question?
Yeah.
We are talking about the clouds, right? We are talking about the helium. So if I want to focus on the quasar, if I want to I want to see the jets of that quasar galaxy. So won't I mix up between the cloud metals, cloud things, and the quasars atoms and all? So how do I differentiate between them?
Okay. So if you're looking for the quasar directly, so we have different surveys that looks for the quasars and that those directly probing that jets and the central engines of the active galaxies, like the accretion disk and the jets. But what we are doing here is we are basically studying the baryonic composition, like how a galaxy interacts with its outskirts, like the outside environment, where most of the baryons are residing in a diffused state, like a diffused gas, which can have hydrogen and other metal lines as well. So, like,
so can't we distinguish? I mean, if I am seeing the quasar like the jets directly, so how do we distinguish between the
using the spectra, like if you directly see the quasar, we see continuum and the emission lines, like broad emission lines and narrow emission lines, because quasar are very bright source in our universe, and they have a active central engine, which is a accreting supermassive black hole. So they have jets and accreting disk, which accretes the gas. So if we're directly looking at the quasar spectrum itself, so we see continuums and very broad and narrow emission lines. So what we are seeing is the absorption feature, because if something comes in between that spectrum, so it will absorb some of the light. So we are seeing at the absorption spectrum, not at the emission or continuum spectrum. So that's how we distinguish that there is something in between, which giving rise to this absorption feature. Did you
Okay,
get?
thank you.
Did you get it?
Yeah, I got it.
So now, so far we have like studied the gas properties, like what the column density and Doppler parameter of the gas, and we've used the data for gas from the cost to study the gas parameters. Now we want to relate it to the galaxy, like to which galaxy this gas cloud is relating, which is correlating, and so we used keeping this instrument detail. So we used news data, which is installed on the very large telescope. Yeah, this is what news will look like. So what news does? Okay, I have to just give a brief detail. What news does is news basically looks at a patch of sky, like I can show here. Like what news does, it looks at a patch of sky. This is a two-dimensional image of the sky, which gets sliced on the sky, and again it gets sliced according to the wavelength into different components, which is this spectral dispersion. And then what news does is it stacks at each wavelength, and it's create a cube, and for each 2D pixel we have an image of that object, and the third axis gives the spectrum of that image. Like you can see here, there are two spatial axes which gives rise to a image of that uh, object, and the third axis gives rise to the spectrum of that object. So now what we are looking is the 2D thing of that 3D cube. Like it's basically a 3D cube, but we use the software to load this 3D cube, and we do a median of all the stacks. Like there are several stacks from one wavelength to the end of a wavelength, one start and the end, and we stack like to see what other extended sources are here. So we see different extended sources here. So how we identify between the extended sources and the continuum or constant sources by looking at spectrum either or a point spread function. Right? If the point spread function is circular, then we say that this is not extended source, it's a star or something. Or also the star has some black body kind of feature spectrum. So we can also look at the spectrum, and if we look at the spectrum, so the extended sources, which are mostly the galaxy, will show some prominent emission lines, like for say O2, O3, H alpha, H beta. There are different emission lines. So that's how we conclude that this is a galaxy and this is a star. So since in the field there are several galaxies, so I haven't studied all of the galaxies because that's not we are interested in. We are interested in the galaxies which are near uh, to our gas cloud, which is our absorber. So here three is the galaxy which is near, like coinciding with the absorber redshift, which is 0.39047. And this one I marked is for just to as an example of study, like to mention that how we conclude that this galaxy is not coinciding with the absorber redshift. Exclude this PSF subtraction. I will tell why we need a PSF subtraction. PSF subtraction is basically like quasar is a very bright source, so it will dominate over the source of the galaxy. Like here we can see near This is the quasar, and we are not able to see any galaxy here. Okay, because the quasar is so bright, uh, we are not able to see the galaxy. The galaxy is hidden behind that quasar. So galaxy light is very prominent. So that's why we need a PSF subtraction. PSF, what it does is basically removes this quasar light, from this cube, from the pixels, and after the removal of the quasar light, we were able to fully resolve a galaxy, see a resolved galaxy, like here as we see. You can see the better picture. This is a zoomed in picture. Like like you can see, after removing this quasar light, we are able to see this. There is a galaxy just below the quasar. This is the another galaxy which is very near or coinciding with the absorber structure. So these white pixels are, don't confuse it, this if this is a galaxy or something. This is some residual. Like when we do a quasar subtraction, like when we try to remove the full quasar light, so in the process there are some residuals remains. Like it's not very 100% perfect or efficient. So these white pixels are just representing that residual is there. So you can see the spectrum here of the galaxy, the G0. So as you can see from the redshift itself, it is near to our absorber's redshift, because our absorber's redshift is 0.39047. So this spectroscopic study of galaxies is uh, very well required, because from the spectroscopic study we get to know the redshift of the absorbers. If anyone wants to know how we calculate it, I can tell it later, like how we calculated with redshift. So by doing this spectroscopic study, we get redshift of the galaxy, and we already know the redshift of the absorber. So from comparing the redshifts of both absorber and the galaxy, we can say like the absorber is near to this galaxy, or the galaxy is coinciding with the absorber's redshift. So trust me, as you question, like you can see, there are mostly the prominent emission lines. There is very less absorption features we are seeing. Like these are the purple lines are the emission lines, and these orange lines showing the absorption features. So this is the emission line, and the blue and the orange lines are showing the absorption features. The spectra is a little bit weird. Like there are very spikes here and kind of dirty spectra. This is because these are mostly the skylines. So we are not able to mask all of the skylines. So this is how we see like a zoomed in picture of where Pluto is coinciding. Same as for other galaxies. G3, this is the another galaxy which is like coinciding with the absorber redshift. This is its one of the prominent emission line. So this one that I marked with one as the G1, which I said that this is not coinciding with the absorber's redshift, and this is how we conclude. Like see the redshift of this galaxy, it's 0.33803, which is quite far from the absorber's redshift, which is 0.3904. So after calculating the redshift, the spectroscopic redshift, we calculated different parameters like velocity, offset, angular separation, and impact parameter. What all those means is like velocity offset is basically like we have two astronomical objects. We know the redshift of both astronomical objects. So velocity offset basically defines the velocity difference between those two objects corresponding to their redshift. Okay, like we know the redshift, but we can't say how much they are differing. So we convert those redshifts in a velocity form. So you can see that G0 is quite near to the absorber, and G3 as well. And what angular separation is, like if you see it in the sky, if you look at two astronomical objects, so both are at a different position. So you have a two different line of sight. So the angle between those line of sight is this angular separation, which basically defines the angle between the line of sights of those two objects. And the impact parameter is just uh, projected separation of these two astronomical objects in the plane. Like from angular separation, we see the angle between this line of sight. But if you want to look at the separation in a plane, uh, so that's how we get the impact parameter, which is calculated using this angular separation itself. So what I want to emphasize is look at this G1. Even the impact parameter is not that high, but this velocity offset in the redshift, in the absorber's redshift is very high. So that's how we conclude that this particular galaxy G1 is not associated with our absorber. So that's how we conclude that the importance of determining the spectroscopic redshift. So far we have studied the physical properties of the galaxies, how the column densities look like, what are the different ions present there, and we've also studied the associated galaxies. There are some very basic parameters. So now coming to the modeling part, which basically used to study the ionization structure of the gas. So this part is quite involved. So for this, we use there is a already a well-written code which is known as Cloudy. It's a radiative transfer code. It does radiative transfer calculations over a gas cloud. So what it does basically, uh, we assume the gas cloud as a plane parallel slab of gas, like an infinite plane parallel slab. But the width is defined, okay, because the gas is highly ionized. So to study this ionization of the gas, we simulate clouds in this cloudy model. So we run photoionization equilibrium models in cloud. So what photoionization equilibrium is like, if there is a gas cloud, so assume there is an extragalactic UV background. So there are UV photons which are coming and striking that gas cloud. So ions present in that get ionized by hitting of those UV photons. So that is known as photoionization, and it ejects some electron. And simultaneously, a recombination is happening, like the electrons which got ejected, and they again recombine to the another ion, and the neutral ion again forms. So the balance where the number of photoionization and number of recombinations per unit volume matches, like they comes in equilibrium state. That is known as the photoionization equilibrium. So we then so what we give as in the input is the UV background radiation. This blue lines are showing the UV background radiation, and this width is defined by the H1 column density of the cloud. This basically limits the size over which the cloudy has to run its radiative transfer calculations. And this H1 column density we have already inferred from our observations by doing wide profile fittings. Okay, so what we give is density and metallicity, like the number density of the hydrogen atoms present in there and the metallicity. We give a grid of metallicity and this density so that cloudy can run over that grid. So it will run over a 2D grid, like it will be a like this a 2D grid, like for each number of density, or each number of density it will run for different metallicity and then come to number different density and then run for a, this is, let's assume Z, and this is NH. Okay. So we have to assume that uh, we have a uniform metallicity and density, then photoionization and thermal equilibrium with this extragalactic UV background radiation. Okay, so the cloudy will do the ionization equilibrium, thermal equilibrium calculation, and it will perform some radiative transfer calculation and results in a column densities of all metal ions. Like it will give us a very big array of column densities of all metal ions and equilibrium temperature. So what we are interested in studying these column densities, like to constrain this column density. So what we do, like let's say for example, O6, it gives an array, a big array of the column densities which have different numbers. Like for example, let's say 11, 11.2, 11.5, and something and so on. So what we want to compare this output to the column densities of our observations. Like I showed that we did some void profile fittings and we got some column density numbers of particular ions, metal or hydrogen. So these are our observations. Like for say example, like we got a column density of something 18.53 for hydrogen. So that is our observational quantity of the column density. But what cloudy is giving is an array, a big array of the column density. So we want to compare this. So to compare this, we use a statistics, which is the Bayesian statistic. So we use some Gaussian likelihood and compare the column densities of different ions, metal ions. So for this, we use maximum likelihood solution and perform a MCMC technique because it can handle multi-dimensional models since it's a multi-dimensional on a grid of metallicity and density. So we use a multi-dimensional approach. So this is what a very preliminary result, which is not finalized yet because we are not able to constrain this hydrogen number density and metallicity properly. Like we can see the constraint properties. So these are some pretty numbers that we got after constraining with this, the output of the cloudy and our observation. So why this number is not very well constrained? Because we have a less number of observations. Like we identified few metal ions. So to very well constrain this number density and metallicity, we need more ions, which we don't have right now. Like a proper measurement, proper observation on the different metal ions. But what we have is lower limit on the column density of various ions, not the actual measurement. So we need to incorporate these lower limits and upper limits to finally constrain this metallicity and the hydrogen number density. Yeah, okay. That's from my side. Thank you guys.
So thank you, Shubham.
Yeah.
Uh, and thank you everyone for attending the meeting.